this is a example of searching for text. If you have used grep command on Linux, this command actually searches the occurrence in the file. Basically, locate every occurrence of an input string. We call them a keyword or a pattern to search. And for example, let's say we have a we have 4 keywords. We put them into a string or array of characters in this way. That is the first keyword, with is the second, and then have, and then from. So we have these 4 keywords we would like to search in these input text. And you can easily implement or call the command grep using one of these keywords and search on a given text or text file. We can perform this using brute force search using 2 input strings. And this is the string we store the patterns, the keywords, and then we move this source text along this horizontal axis, because it will move this string 1 letter at a time. Then we'll perform comparisons on these 16 characters. If there's a match, we will produce FF and F on all these locations to indicate that's exactly the keyword we're searching for. Or if that's not a match, we'll output zeros on those 4 locations. We're actually going to use these 2 variables in our OpenCL program. But this is the idea of that if you perform this as a brute force search, and you can basically move these input strings 1 character at a time and perform this brute force matching. Okay, so here I want to describe what we're gonna actually do in one work item. So we would like to perform the following in a work item on an OpenCL device. We would like to test the resulting vector to determine whether or not the pattern words were recognized. Like we do comparison in the previous slide, we're going to match the input data, whatever input file or text strings that you are given to the work item is given, and then match with the keywords. It will, if there's a match, it will not immediately produce a key value pair. If it does that, you have to report all the match to the reduce stage. So instead, what we're going to do is it will increment a counter in the local memory corresponding to the word. So in this case, we have 4 keywords to search. We have that, with, have, from. So we'll give a counter for each of these keywords. So we will increment a counter in local memory corresponding to the keyword. In doing so, it does both mapping and this local reduction. So the point I want to make here is that it's not a typical mapping stage where you have the keyword produced and stored, and then you have later another reduction processor to process it. Instead, we have this simpler mapping, but with a local reduction stage. So that for each work item, it will check if there's a match. If there is a match, it will increment this counter in local memory for that corresponding keyword. And it will perform this until all the input strings are processed. So we're basically going to look at the input string text one character at a time to see whether they match the keyword or not. Once that's done, and then we'll pick one of the work items in this group to add the local results to the global result. And finally, the final reduction is done with the one of the work items. So I want to use this diagram to show you a bit more what we mean by that. Okay, so what we have here is the input text. Okay, I just put in some random text. This book is from a collection of 1,000 books. And the diagram here shows that we have some work items. I use M00, M01 to indicate those are the two work items in group 0. And I use M to represent its mapping stage. Instead, it's mapping and local reduction. But these two are in work group 0, and these two are in work group 1. Now, physically, when you execute these, or these 4 work items, they could be on different computer units. So in this work group, we have 2 work items, and we will give each of these work items some pieces of this original text. So in fact, because we have 4 work items, I divide the text into 4 equal-sized pieces, 3 lines per work item. For each one of these work items, it will do matching on these input text. So basically, you can move the input text along the horizontal line to match with those 16 characters that we showed earlier, where we have the 4 keywords. And it will perform this character by character comparison to see if there is a match. I don't explain how it actually does that, but that's the point. So this input data will be processed by this work item to perform these character by character match. If there's a match, this work item, let's say if it matches with the first keyword, I think that's from? No, that's the last one. Anyway, one of the keywords. If there's a match, let's say the last keyword is from, I remember that, then this work item will increment this local result. This is a counter for the last keyword from. If this work item finds there's an occurrence, it will increment that counter by 1. Similarly, if it finds that, then they'll increment the counter 0 by 1. So this work item 0 actually performs the mapping and local reduction in one shot, or in one work item. At the same time, this other work item in the same work group will perform the same thing, but it works on a different piece of the original text. It'll match these input text with the 4 keywords and increment the corresponding counter by 1 if it finds a match. And the same thing happens on work group 1, represented here using different color. It also has these 4 counters that will eventually have the number of occurrences of these 4 keywords in these 2 pieces of the original text. And then this work group 0, one of the work items will use the final result to update the global result. The same thing for the work group 1. So it still follows this MapReduce paradigm, but there are several things we need to think about. One thing I want to point out here is that when these work items try to increment these counters, one thing we have to do is to really initialize the counters to 0 before you can properly increment them. So how do we do that? And even before that, how do we allocate this memory in the local memory space to store these counters? And we need to allocate the space, and we need to initialize these 4 counters to be zeros, so your later counting could be correct. Otherwise, you'd be having corrupt data, corrupt counters. So that's something we need to think about. Actually, I have a whole list of the things we need to think about. How to synchronize work items. So what if, let's say you can have one of them to initialize these counters to be zeros, but because these work items, they work independently, how do you make sure that none of them will start counting before the counters are initialized to 0? If you not guarantee that, then some of them maybe start counting even before the counters become 0. Then you initialize them to 0, so the previous counting are kind of missing. So that's one thing. And what if 2 or more work items attempt to increment the same counter? You would think that they will increment the counter by 1 and 1, then you have 2. But think about that. You are doing a read, add, and write operation when you increment the counter. You have to read the value from the original counter, increment it, then write the new value back. And then you have to make sure that these 3 operations are going to happen in one shot. If, let's say, you have 2 work items, they both read, they're going to be reading the same value, they both add, you're going to be adding, we increment the original value by 1, and then they write the value back. So instead of incrementing the value by 2, you end up having the new value 1 more than the original value, and that's bad. Okay, so next things we want to think about is how do we synchronize the final reduction stage? What if the final reduction stage starts before all the work items finish their counting? So you have these work items, you can synchronize somehow within the work group, but across work groups, how do you know by the time you perform the global reduction, you are sure all the work items are finished? That's important. Otherwise, you're going to miss some of the counts. And I said this earlier, how do we initialize local memory? How do we, because in-queue write buffer is the one you can use to initial values in the global memory, but that does not work for the local memory. So how do we do that? I want to introduce this barrier and atomic operations to address some of the problem that we outlined earlier. Barrier operation is an operation that based on memory access. This barrier operation supports so-called read or write fence. The purpose is that with barrier operation, we can ensure that all memory accesses preceding the barrier are executed before any work item can continue executing. And that's going to be very helpful to us, as I'm going to show you, because this barrier operation will kind of block all the, will prevent all the work items from proceeding to the next stage until the preceding memory operation is done, is completed. So let's say if we want to initialize the counters, the local result counters, we write zeros to these counters. We can put a barrier so that we all the work items have to wait until this write operation is completed. And also we can apply that barrier using the global memory fence. This is going to take effect on all items that are going to access global memory. So it will make sure that global memory access is completed before the work items can proceed. The other operation is atomic operation. Atomic operation is guaranteed not only to that a write update occurs, but also the read and write are combined with some other operations and the data occur without interruption. So what this really says is that if you, let's say you have a increment, you're supposedly going to do read, add, and write back. Because we have this atomic operation, these three operations will occur either all together or nothing at all. So this increment operation cannot be interrupted or interleaved with other operations. So that's the purpose of this atomic operation. And as you can see, with this atomic operation, we don't have to worry about, what if two work items are attempting to increment the same count. If this is supported by the hardware, which really it is, then we don't have to worry about this situation where you have this contention of writing or updating the values in memory. There are several atomic operations. We're going to actually use one of them in this example. It's called atomic add. It will be able to increment the value in the memory using the memory pointer.